Here we have two Faraday's laws. Faraday's first law as well as Faraday's second law. So generally this shows whenever the corresponding electrode reactions occurs, how they are related with reference to their corresponding charge which is used. So there is nothing but how much of the quantity of the substance is deposited or released or evolved. The corresponding electrode potential whenever certain charge is utilized in the corresponding electrode or the corresponding reactions. So coming to the Faraday's first law. According to Faraday's first law, in the corresponding electrode reactions, the amount of the substance that is deposited or released or evolved is directly proportional to quantity of the charge that is used in the corresponding reactions or electrode process. So if I take the mass of the substance that is deposited or released or evolved as M, so as per definition this is proportional to Q. Q is the charge which is used in the corresponding electrode reactions or the process Q. So from this we can have, in order to remove this proportionality, we'll multiply with constant here, this we use it as E, small e into Q, where small e is called as electrochemical equivalent. Electrochemical equivalent. So this is a mass of the substance that is deposited or released or evolved at the electrode reaction or the electrode, and E, small e is the electrochemical equivalent and the Q is the charge in coulombs. So in general, so Q is nothing but the product of current into time t. So current in amperes, time in general in seconds. So if you replace this with, we can have the expression as M is equal to E into I into T. So we make this as equation 1 just for our convenience. We make this as equation 2. Suppose if we want to define the electrochemical equivalent, in order to define this, you take the value of Q as 1 coulombs. If I take the value of Q as 1 coulomb, from this expression 1, we can make M is equal to E. So from this, we can define what is E. Nothing but the electrochemical equivalent of the substance is nothing but the amount of the substance that is deposited, released or evolved at the electrode when 1 coulomb of the charge is used in the electrode process. That's how we can define the electrochemical equivalent. This is nothing but the mass or the quantity of the substance that is released or evolved or deposited at the corresponding electrode when we use 1 coulomb of the charge in the process. Then we can call this as electrochemical equivalent. Electrochemical equivalent. At the same time, for example, I am taking a metal ion which is sodium ion. The sodium ion, by taking 1 mole of electrons, it will deposit or it will release about 1 mole of the sodium metal. Or else if you take the magnesium, this magnesium ion, by taking 2 moles of the electrons, this will release or form 1 mole of the magnesium. Here we are saying 1 mole of the electrons. Definitely this 1 mole of the electrons will carry certain charge. The charge carried by 1 mole of the electrons is generally 96,500 coulombs, which is nothing but product of the charge of a single electron and the Avogadro number will give the total charge carried by 1 mole of the electrons. So charge of electron is 1.6 in 10 power minus 19 coulombs, that is 1.602 into 10 power minus 19 into the Avogadro number 6.023 into 10 power 23. So this is the charge of one electron in coulombs. As we are saying, 1 mole of the electron means generally as per stoichiometry, 1 mole of the substance generally should have the Avogadro number of the particles. This is the charge of the single electron. The product of this will give the total charge carried by 1 mole of the electrons, which is nothing but 96,500 coulombs. This is nothing but 1 Faraday. So simply Faraday means it is the charge carried by 1 mole of the electrons. Now as per this discussion, see in the second case, here I am using 2 moles of the electrons. So what is the charge carried by 2 moles of electrons? I can write it as 2 Faradays. 2 Faradays. That means 1 mole of the magnesium ions. By taking 2 Faradays, we are getting 1 mole of the magnesium. The mass of the magnesium which is deposited at the representation is, it is 24 grams. Nothing but gram atomic weight of the magnesium is 24. Suppose if I take only 1 Faraday, this divided by 2, this also divided by 2, that means you get only 12 grams of the magnesium. You take another example, you take aluminum, Al3 plus ions. 1 mole of this will be reduced into the corresponding aluminum metal by taking 3 moles of the electrons. That means the total charge is 3 Faradays. So 3 Faradays will give 27 grams of the aluminum, because the gram atomic weight of aluminum is 27 grams. If I take only 1 Faraday, nothing but 1/3 of this, we'll get 1/3 of this, 27 by 3, that is 9 grams. Now, as per stoichiometry, this is the atomic weight by 2. Here, what is 2 actually? The charge. Nothing but valency of the metal magnesium. In this case, 27 by 3. What is that 3? Nothing but charge or valency of the aluminum. That means the corresponding atomic weight by valency for the given element or the metal, which leads to give the corresponding equivalent weight. So this is the equivalent weight of magnesium. This is the equivalent weight of the aluminum. So from this I can give a conclusion that for the deposition of the one equivalent weight of the substance, always we require 1 Faraday. So to deposit 12 grams of the magnesium, we require 1 Faraday. Similarly, to deposit here 9 grams, which is nothing but the 1 gram equivalent weight of the aluminum, we require 1 Faraday. So always 1 Faraday is nothing but it is the amount of the substance which is exactly equal to 1 gram equivalent weight. So if you use exactly 1 Faraday, the amount of the substance that is released or evolved or deposited will be 1 corresponding equivalent weight of the corresponding element, whether it is the metal or the non-metal. So from that, so we can replace this particular E value with so as per discussion, 1 Faraday is able to give the mass of the substance as 1 equivalent. So from this, suppose if I take 96,500 coulombs, this will deposit the amount of the substance by E. Here remember, E is nothing but a gram equivalent weight. So if I take only 1 coulomb, so what is substance that is deposited here? E divided by 96,500. Now as per definition here, how much of charge we are using? 1 coulomb. If it is 1 coulomb, how much we are getting here? E. If it is 1 coulomb, how is the mass we are getting here? E divided by 96,500. That means in this particular expression, I can replace E with capital E divided by 96,500 in the equation 1. Therefore, from this we can write equation 1 as M is equal to capital E divided by 96,500 as usually this is, and into Q. So small m is equal to equivalent weight of the metal into Q is the charge. But what is Q actually? I into T or C into T. So from that, M is equal to E into I into T divided by 96,500. But what is exactly E here? Nothing but equivalent weight of the metal or the element, which is given by its atomic weight by the valency. So here E is nothing but A by Z, where Z is the valency. So if you substitute this here, finally we can get the expression as, so M is equal to A into I into T divided by Z into 96,500. This is the final expression for the Faraday's first law. So from this we can do the many problem part here. So anyway, what is A here? A is the atomic weight or gram atomic weight of the element, and I is the current in amperes, T is the time in seconds, and Z is the valency of the corresponding metal or the element. This is Faraday's first law. Then let's go for Faraday's second law. According to the Faraday's second law, whenever we take different electrolyte solutions which are connected in series and use same quantity of the charge throughout all the corresponding solutions, then according to second law, the amount of the substances which are deposited, released or evolved will be proportional to their equivalent weights. Proportional to their equivalent weights are the gram equivalent weights. For example, let us take different electrolyte solutions. So the first solution, assume we have copper sulfate, aqueous solution. So assume two electrodes here, anode and cathode here, and take another solution which is having the dilute sulfuric acid H2SO4, and take another solution which is having aqueous solution of silver nitrate AgNO3, silver nitrate. Now here also we have the electrodes, anode as well as the cathode. So these three solutions are present in a series, okay, and so these are connected externally like this, externally. Now we have to use the same quantity of the charge throughout all this. Then according to the Faraday's second law, mass of the substance which is deposited or released or evolved in every corresponding cases will be proportional to their equivalent weights. Here the products what we are getting, the corresponding electrodes will be at cathode, copper we are getting, but at anode we get oxygen, O2 gas. And coming to this case, the cathodic product is hydrogen gas, and the anodic product is oxygen gas. Third case, the cathodic product is silver, the anodic product is oxygen. That means the respective cases we have here sulfate, here also we have sulfate, we have the nitrate as the anions. So these are multi-atomic ions. So these do not participate in the electrode reaction because they require large amount of the deposition potential, so which is not exactly available at the given circumstances. That's why as we are using aqueous solutions in the respective cases, from that the corresponding water will split into or to gives the corresponding oxygen here, here also oxygen here, here also oxygen here. That means all these three cases, the anodic product is oxygen. But coming to the cathodic product, in this case it is copper, it is hydrogen, it is the silver. That's why as per the first thing here, the mass of the copper is proportional to equivalent weight of the copper. The same time, the mass of the oxygen is proportional to the equivalent weight of the oxygen. The second case, the mass of the hydrogen is proportional to equivalent weight of the hydrogen. The third case, the mass of the silver is proportional to equivalent weight of the silver. That means in overall we can say here the mass of the corresponding substance is proportional to its equivalent weight. So in general, M1 by E1 is equal to M2 by E2 is equal to etc. This is general expression what we can say for the Faraday's second law. So ultimately we have to take different electrolyte solution. They should be connected in series. According to Faraday's second law, the mass or the amount of the substance which is involved at the electrodes will be directly proportional to the equivalent weight of the corresponding substance. This is Faraday's second law. There are the two laws what we have in the electrochemistry, Faraday's first law as well as Faraday's second law. Yeah, let us see, the next one is conductance. So here we are discussing mostly about the electrolyte solutions. So whenever you place an electrolyte in corresponding suitable solvent like water, the corresponding electrolyte will split into the ions, cations and anions. So these cations and anions will undergo mobility. So this leads to give the conductivity for the corresponding solutions. And before that, we will understand, before we go into this, let us discuss other aspects also. Here, according to Ohm's law, if I take the resistance as R, so the resistance is proportional to length of the corresponding solution and also the cross-sectional area. Yeah. Basically, in order to get this conductance here, we cannot directly attach this corresponding electrolyte compound into the corresponding electrodes directly because it won't perform any conductivity. So in order to have the conductivity or conductance, we have to place this corresponding electrolyte in the suitable solvent. Then only it will form the corresponding ions. The ions on mobility gives rise to the concept conductivity or the conductance. So that's why, suppose you take a container or a vessel which is having the length L, its cross-sectional area or so resistance is proportional to or directly proportional to length and inversely proportional to the cross-sectional area. So R is equal to L by A, or this particular R is given by, that means here we are removing this proportionality. So we have to multiply with one constant here. This constant here it is rho into L by A, where R is the resistance. We call this rho as a specific resistance. Specific resistance or resistivity. R is the resistance rho is specific resistance, or also called as resistivity. But as per IUPAC, we have to use this. Instead of specific resistance, we have to use generally resistivity. And L is the length and A is the cross-sectional area. Cross-sectional area. And generally the resistance have the units as ohm. And this length L have the units as centimeter. The A have the units as centimeter square. So from this we can have the units for the rho as, so R is units of ohm into centimeter divided by centimeter square. So from this the units for this rho as ohm into centimeter. Ohm centimeter is the units for the resistivity. The same way, take the equation, make it as equation 1 here. You take the reciprocal of this R. That means we can have 1 by R will be equal to A divided by rho into L. Rho into L according to this. So here actually this particular 1 by R, reciprocal of R, actually R is a resistance. This 1 by R is generally called as G, which is conductance. Conductance. G, you can also use it as C. So G is equal to, this particular 1 by rho is called as K into A divided by L. So actually rho is the resistivity, and here this K is called as conductivity. Conductivity. So actually, so G is the conductance. This K is conductivity. Conductivity. So from this we can define this particular conductivity. So how to define the conductivity? Of course, we can also call this conductivity as specific conductance. Specific conductance, but as per IUPAC, we have to use conductivity only, not the specific conductance. Conductance. Okay, and in order to define this K, now just I am taking here the A or the cross-sectional area as unity, nothing but 1 centimeter square or 1 meter square. 1 centimeter square or 1 meter square means I am taking unity. This A value is 1 unity, and this L or the distance also I am taking as unity. If you substitute this A as 1 and also L as 1, so we can get this G is equal to K. Yeah. In the expression 2, if I take the value of A as 1 centimeter square and the value of L is equal to 1 centimeter, this particular expression 2 we can write it as G is equal to nothing but K. From this we can define K as the conductivity of the corresponding cell is nothing but its conductance of unit volume having any amount of the corresponding solute, because A is the area, L is the length, so area into length will give the volume. Area into L will give the volume. That's why whenever we want to define this particular K, nothing but the conductivity, nothing but conductance of the solution having corresponding unit volume of the desired substance. Or we can also define this in different way also. The conductivity is nothing but conductance of the solution having the two electrodes separated by a distance of 1 unit and cross sectional area of each electrode is 1 centimeter square. So when these two are separated by 1 centimeter and cross sectional area is 1 centimeter square for the corresponding electrodes, then the conductance of this particular electrode solution is generally called as the conductivity. So we can define in different ways. This is how we can get the K. Generally we can also actually call this as K as kappa. K is actually, should call it kappa K. This is how we can get the conductance. Okay, and generally the conductance here we are taking any quantity of substance. Suppose if I take the resultant solution is having 1 mole of the solute, only 1 mole of the solute. That means here assume we have the volume of solution as 1 liter and the corresponding solution is having 1 mole of the solute. In such a case, the conductance we can call it as molar conductance. Molar conductance, which is conductance. So we can show like this. We can call this as lambda m. Here m stands for molar. So molar conductance. So here this is related to the conductivity as, so molar conductance is equal to conductivity K into the volume of the solution. Of course, we can also call this V as the dilution. Dilution is how the relation between the molar conductance and conductivity are related here. So this is nothing but equal to conductivity into volume of solution or the dilution. Here we are defining the molar conductance. That means as per molarity, so M molarity is equal to number of moles by volume of solution in liters. And as per definition I am saying here, only 1 mole of the substance is present here. That means in this number of moles is nothing but 1 mole. At the same time, we can also modify the expression as N into 1000 divided by volume of solution in ml. So molarity expression here. So from this, how to get the V value here? So V is nothing but N into 1000 divided by the molarity of the solution. As per this definition, the value of N is equal to 1. The value of N is equal to 1. So we can write this particular expression like this as, so here the V is equal to 1000 divided by molarity. So you replace this V with this value. So we can have the expression as the molar conductance is nothing but K into 1000 divided by the molarity, nothing but concentration. And in the case of saturated solutions at the given temperature, we can also replace this with the solubility. So that's why whenever we have the molar conductance here, that is related to the molarity like this. So molar conductance is equal to K into 1000 by molarity of the solution. And from this expression, one can understand that this lambda m, nothing but molar conductance is directly proportional to volume. Here addition of solvent, we generally call it as dilution. So on dilution, the volume increases. So automatically this molar conductance also increases. At the same time, here we are saying dilution means concentration decreases. At the same time, this conductivity is inversely proportional to volume. More dilution means smaller is the concentration and less dilution means higher is the concentration. So from this we can compare what happens to the corresponding molar conductance as well as conductivity on dilution, otherwise on change in the concentration of the corresponding solutions. This is about what is molar conductance. At the same time, if we use only 1 gram equivalent of the solute. Only 1 gram equivalent of the solute in the resultant solution, then the conductance is generally called as equivalent conductance. Equivalent conductance. So it's nothing but the conductance of the solution having 1 gram equivalent of the solute. So which is lambda equivalent or equivalent conductance is given by K into 1000 divided by normality of the solution. Normality of the solution. This is how we can show relation between this equivalent conductance and corresponding conductivity K. So there is a small difference between molar conductance and equivalent conductance. In the case of the molar conductance, amount of the substance we are using as 1 mole. In the case of the equivalent conductance, the amount of substance we are using 1 equivalent of the substance. 1 equivalent of the substance. So here we have an idea that normality is equal to valency factor into the molarity of the solution. That's why we can also write the expression as the equivalent conductance is nothing but K into 1000 divided by valency factor into the molarity. So these we can use accordingly to solve the problems. This is based on the concept of the stoichiometry, especially strength of the solutions or the concentrations of the solutions. Now, if we draw the graph between the molar conductance, which is the molar conductance lambda m, and the square root of concentration. In the case of strong electrolytes, it is observed that we will get the graph like this. Otherwise, you make it as a line here, we will get the graph like this. And on extrapolating this particular graph, what we can get is this particular line will touch somewhere here. So this will give the molar conductance at 0 concentration. Instead of 0 concentration, we can also use the term infinite dilution. Infinite dilution. That means in the case of the strong electrolytes, this is the strong electrolyte. If you take a weak electrolyte, suppose take acetic acid, we will get the graph actually like this. This is for weak electrolyte, like acetic acid. In such a case, on extending this, we may not get exactly this graph which will touch the particular axis, y-axis. That means, in the case of the strong electrolytes, we can get this lambda naught m by extending the graph like this. But in the case of the weak electrolytes, it is not possible to get the particular value of lambda naught m. This is for weak electrolyte. It is not possible to get graphically. That's why in order to avoid these kind of uncertainties, Kohlraasch law has been introduced, which is used to find out the equivalent conductance of the corresponding weak electrolytes at the infinite dilution. Equivalent conductance of the corresponding weak electrolytes at the infinite dilution. So we can also call that conductance as limiting conductance. Limiting conductance of the corresponding solution.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.